Welcome back to AI.Code.Cast. Today, we're doing a deep dive into a challenge that kind of feels like it's straight out of a sci-fi movie.
Yeah.
Picture this, right?
Mm-hmm.
You got a robot.
Mm-hmm.
It's navigating a minefield.
Oh.
But instead of dodging explosives,
Right.
it's trying to find the shortest path while disarming the fewest mines.
Okay.
So that's basically the problem we're tackling today. Navigating a grid with obstacles and figuring out like the fewest obstacle removals to get the shortest path.
I see what you mean. So it's not just about finding any path.
Yeah.
It's about optimization, right?
Right.
Finding the best path possible.
Exactly.
Like, think about it. You're designed on a self-driving car,
Okay.
and it needs to navigate a city grid with road closures.
Right.
You wouldn't want it to take like a super long detour
You know.
if there's a way to clear a path with just a few adjustments.
Yeah, that makes sense.
That's the kind of real-world scenario we're modeling here.
Okay, so let's break down the problem itself.
Huh.
We've got this grid. Think of it like a chessboard.
Mm.
And each square can either be empty, which is represented by a 0, or blocked by an obstacle, represented by a 1.
Okay.
Our little robot buddy starts at the top left corner,
All right.
and the goal is to reach the bottom right corner.
Okay.
The catch is the robot can only move up, down, left, or right.
Okay.
No diagonals allowed.
Gotcha.
So it's like navigating a maze where you can only make 90-degree turns.
Right.
And we need to figure out which obstacles to remove
Uh-huh.
and how many
Yeah.
to give it the most efficient journey.
I see.
Right. So how do we even begin to approach this? Like, my first instinct is to just try every single possible path
Oh.
and see which one requires removing the fewest obstacle.
Yeah.
Like brute forcing our way through.
That's a valid thought, and that's actually what we call the brute force approach.
Okay.
It might work for like really tiny grids,
Right.
but imagine a massive grid, say 100 by 100.
Oh, wow.
The number of possible paths becomes astronomical.
Yeah. Trying them all would take forever, even for a supercomputer.
Yeah.
That's why we need smarter, more efficient algorithms.
Okay, I'm starting to see the challenge here. Brute forcing isn't going to cut it for anything beyond a tiny grid. So what are our options? What kind of algorithms can help us find the optimal solution without spending a lifetime computing?
Well, there are a couple of clever approaches that come to mind,
Okay.
and both of them have been used successfully by folks tackling this challenge.
Okay.
The first one is called Dijkstra's algorithm,
Okay.
a classic in the world of pathfinding.
All right.
The second is a modified version of breadth first search,
Okay.
or BFS,
Mm-hmm.
using a special data structure called a Deque.
Ooh, Dijkstra's algorithm.
Uh-huh.
I've heard of that one. Isn't that used for finding shortest paths on maps and stuff?
Exactly.
Mm-hmm.
Dijkstra's algorithm is all about finding the shortest path in a weighted graph.
Okay.
Now, you might be wondering, how does a grid become a graph?
Yeah.
Well, imagine each cell in our grid is a point
Mm-hmm.
or a node
Okay.
in our graph.
The connections between adjacent cells
Right.
become the edges of our graph.
And the weight of each edge represents.
The cost of moving between those cells,
Okay.
if it's an empty cell,
Yeah.
the cost is 0, since our robot can move freely.
Okay.
But if it's an obstacle,
Right.
the cost is 1, because that represents the effort of removing the obstacle.
So Dijkstra's algorithm will essentially explore this graph, always looking for the path with the lowest total cost, which would mean removing the fewest obstacles.
Precisely. It's like a master navigator constantly weighing its options
Yeah.
and choosing the most efficient route.
Okay, I'm starting to get the gist of Dijkstra's algorithm. But before we dive into the details,
Yeah.
let's touch on that other approach you mentioned, the modified breadth first search with a Deque. What's so special about this one?
Well, BFS is another classic pathfinding algorithm,
Okay.
but this particular version is optimized for situations where the cost of moving is either 0 or 1, just like in our obstacle problem. And that's where the Deque comes in. It's a special kind of data structure that allows us to prioritize how we explore the grid.
Prioritize, what do you mean?
Imagine you're exploring a maze.
Okay.
And you have the option of going down like a well-lit corridor or squeezing through like a narrow, dark tunnel.
Yeah, I'd probably take the corridor.
Right.
Yeah.
That's what the Deque lets us do in our algorithm.
Okay.
It lets us prioritize exploring the empty cells,
Okay.
ones with a cost of 0,
Right.
before we resort to removing obstacles.
Gotcha.
The ones with a cost of 1.
Oh, I see. So it's like the algorithm's intelligently choosing the path of least resistance.
Exactly.
Going for the easy wins first.
Exactly. And this clever prioritization can actually lead to a more efficient solution than Dijkstra's in certain cases.
Wow, this is all really fascinating. I'm starting to get excited about the possibilities. But I think we've covered a lot of ground in this first part.
Yeah.
We've laid out the problem, discussed the pitfalls of brute forcing, and introduced two promising algorithmic approaches.
Indeed. And in part 2, we'll roll up our sleeves and dive deeper into how these algorithms actually work.
Okay.
We'll break them down step by step and even try to solve a simple example together,
Sounds like a plan.
just like we would in a real AI.Code.Cast session.
Awesome. Join us next time as we unravel the mysteries of Dijkstra's algorithm and the magic of Deque-powered breadth-first search.
I'll be here. Welcome back to AI.Code.Cast. Let's pick up where we left off, diving into the nitty-gritty of these algorithms.
Okay.
We'll start with Dijkstra's algorithm. Remember, it's all about finding the shortest path in a weighted graph. And as we discussed, we can think of our grid as a graph where each cell is a node, and the connections between cells are edges with weights of 0 or 1 representing the cost of moving.
Okay, so we've got our graph set up, but how does Dijkstra's actually work? Does it just randomly wander around until it stumbles upon the destination?
Right. Not quite. Dijkstra's algorithm is very methodical. It starts at the robot's starting position, which is the top left corner in our case, and it maintains a record of the shortest known distance to reach each cell. Initially, it assumes all distances are infinite except for the starting cell, which has a distance of 0.
Okay, that makes sense. We haven't explored anything yet, so we assume everything is infinitely far away except for where we're standing.
Exactly. Now here's where things get interesting. Dijkstra's algorithm uses a priority queue to keep track of which cells to explore next. Think of a priority queue, like a line at an airport where people with shorter flight times get to go first.
So the cells with the shortest distances get prioritized.
Precisely. We add our starting cell to the priority queue, and then the algorithm enters a loop. In each iteration, it takes the cell with the smallest distance from the priority queue. Let's call this our current cell.
Okay, so it's always picking the most promising path to explore next. The one that seems to be leading us towards the destination with the fewest obstacle removal so far.
Exactly. Now for our current cell, we look at all its neighbors, up, down, left, and right. For each neighbor, we calculate the distance to reach that neighbor from our current cell. Remember, the distance is 0 for an empty cell and 1 for an obstacle.
Okay, so we're basically checking out all the possible moves our robot can make from its current position.
Right. And here's the crucial part. If the calculated distance to a neighbor plus the distance to reach our current cell is smaller than the currently known shortest distance to reach that neighbor.
Hold on, let me think about that. We're comparing the distance of a potential new path to the distance of a path we've already found.
You got it. If the new path is shorter, we update the neighbor's distance, essentially saying, hey, we found a better way to get to you. And we also add that neighbor to our priority queue, so it gets considered in future explorations.
So the priority queue is constantly being updated with the most promising paths, ensuring that Dijkstra's algorithm is always focusing on the most efficient routes.
Precisely. And the algorithm continues this process, hopping from cell to cell, always picking the cell with the shortest known distance from the priority queue and updating distances if it finds shorter paths.
Until it reaches the destination cell, the bottom right corner of our grid?
Exactly. And at that point, the distance recorded for the destination cell will be the minimum number of obstacles we need to remove to get there.
Okay, I think I'm starting to see the beauty of Dijkstra's algorithm. It's like a systematic search that guarantees we'll find the optimal solution. It's not just about finding a path, it's about finding the best path.
Exactly. Now let's switch gears and explore that modified breadth-first search with a Deque. Remember, this approach is specifically tailored for situations where the edge weights are only 0 or 1, like in our obstacle problem. And it relies on the Deque, a special data structure that lets us prioritize how we explore the grid.
Right. The Deque allows us to prioritize exploring the empty cells, those with a cost of 0, before we resort to dealing with obstacles of the cells with a cost of 1.
Exactly. So just like with Dijkstra's algorithm, we start by initializing a distance array to keep track of the shortest distance to reach each cell. But instead of a priority queue, we use a Deque, and we add our starting cell to the Deque.
Okay, so far it sounds similar to Dijkstra's. We're setting things up, getting ready to explore the grid.
Now here's where the Deque magic happens. When we encounter an empty cell during our exploration, we add it to the front of the Deque. This means it'll be explored immediately because the algorithm always processes elements from the front of the Deque.
So it's like we're saying, hey, this cell is easy to move through. Let's check it out right away.
Precisely. And when we encounter an obstacle cell, we add it to the back of the Deque. This delays the exploration of obstacle cells until all nearby empty cells have been visited.
So it's like we're putting off dealing with the obstacles as long as possible, hoping we might find a path that avoids them altogether.
Exactly. By prioritizing the exploration of empty cells this way, we're mimicking the behavior of Dijkstra's algorithm, always choosing the path with the lowest cost. But we're doing it more efficiently because we don't need a complex priority queue with all its sort and overhead.
I'm really starting to see the elegance of this approach. It's so intuitive. Explore all the easy options first,
Yeah.
then deal with the obstacles if you absolutely have to.
It's a clever optimization that's perfectly suited for this type of problem. Now the algorithm continues processing cells from the ductor, prioritizing empty cells, until it reaches the destination cell. And just like with Dijkstra's algorithm, the distance recorded for the destination cell is the minimum number of obstacles we need to remove.
So both algorithms ultimately achieve the same goal, but they do it in slightly different ways, like having two different tools in your toolbox, each with its own strengths and weaknesses.
That's a great analogy. But before we delve deeper into comparing and contrasting these approaches, let's try putting them into practice. I think it would
Mhm.
be helpful to walk through a concrete example together.
I'm all for that. I learn best by doing. Let's take that example from part 1. A 3 by 3 grid represented as 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. Remember, we're trying to find the shortest path from the top left corner to the bottom right corner while removing the fewest obstacles.
Excellent choice. So let's start with Dijkstra's algorithm. How would you approach this grid step by step using Dijkstra's logic? Remember, we need to consider each cell its neighbors, the distances, and the priority queue.
Okay, let me think. First, we represent this grid as a graph, right? Each cell becomes a node, and the edges represent the connections between cells.
Perfect. You're off to a great start. What would the edge weights be in this graph?
Well, if it's an empty cell, the weight would be 0, and if it's an obstacle, the weight would be 1. So, for example, the edge connected the starting cell, 0, 0, to the cell to its right, 0, 1, would have a weight of 1 since 0, 1 is an obstacle cell.
That's absolutely correct. You're really grasping the idea of representing the grid as a weighted graph. Now, what's the next step in Dijkstra's algorithm? What do we do after setting up the graph?
Let me see. I think we initialize a distance array to keep track of the shortest known distance to each cell. And initially, all the distances are set to infinity, except for the starting cell, which has a distance of 0.
You're on a roll. That's precisely right. We assume everything is infinitely far away, except for our starting point. Now, what about the priority queue? How does that come into play?
Yes. The priority queue is how we prioritize which cells to explore next. We add our starting cell to the priority queue. Since it has a distance of 0 and everything else is infinity, it'll be the first cell we explore.
Excellent. You're navigating this algorithm like a pro. So we've set up our graph, initialized our distances, and added the starting cell to the priority queue. What's next? How do we actually start exploring the grid?
Okay, here's where I might need a little guidance. We take the cell with the smallest distance from the priority queue, which is our starting cell in this case, and we look at its neighbors, right?
You got it. We're now at the heart of Dijkstra's algorithm. We're going to examine each neighbor and see if we can find a shorter path to them. What are the neighbors of the starting cell in our example grid?
Let me see. The starting cell has two neighbors, the cell to its right and the cell below it. Both of those neighbors are obstacle cells.
Great observation. Now, what are the distances to reach those neighbors from the starting cell?
Well, since they're both obstacle cells, the distance to reach each of them would be 1.
Exactly. Remember, each obstacle adds a cost of 1 to our path. Now, here's the key question. Are these distances shorter than the currently recorded distances for those neighbors?
Let me think. Initially, all distances were set to infinity except for the starting cell. So yes, these distances of 1 are definitely shorter.
You nailed it. So what do we do now?
We update the distances for those neighbors in our distance array, and I think we also add them to the priority queue, right?
Absolutely. You're mastering the flow of Dijkstra's algorithm. We update the distances and add those neighbors to the priority queue. Now, the priority queue has 2 cells, both with a distance of 1.
Okay, so the algorithm will pick one of those cells next, and we'll repeat the process. Examine its neighbors, calculate distances, and update if we find shorter paths.
Exactly. And we'll keep doing that, always picking the cell with the smallest distance from the priority queue
Until we reach the destination cell, the bottom right corner.
You got it. And at that point, the distance recorded for that destination cell will be the minimum number of obstacles we need to remove to get there.
Wow, this is really starting to click for me. Dijkstra's algorithm is so systematic and elegant.
It truly is. But remember, we also have that other clever approach to discuss the modified BFS with a Deque. How do you think we'd apply that approach to this same grid? Remember, the key is prioritizing those empty cells.
Okay, let me try to wrap my head around that. We start by initializing our distance array, just like with Dijkstra's, right? And instead of a priority queue, we use a Deque.
Exactly. And we add our starting cell to the Deque. Now here's where the Deque special powers come in. Remember when we encounter an empty cell, where do we add it to the Deque?
To the front. That way it gets explored immediately.
Precisely. And when we encounter an obstacle cell, we add it to the back of the Deque, delaying its exploration. So in our example, the starting cell has 2 neighbors that are obstacle cells. Where would we add those to the Deque?
To the back. We want to prioritize exploring the empty cells first.
Perfect. You're getting the hang of this Deque prioritization. Now, the algorithm takes the first element from the Deque, which is our starting cell, and explores its neighbors. In this case, both neighbors are obstacle cells, and they're already in the Deque, so there's nothing to update.
So the Deque now has those 2 obstacle cells. What happens next?
The algorithm takes the next element from the Deque, which is one of the obstacle cells. This cell has 3 neighbors. The starting cell, a cell below it, and a cell to its right. The starting cell has already been visited, so we can ignore it. The cell below it is an obstacle cell, but the cell to its right.
The cell to its right is an empty cell.
Exactly. And where do we add empty cells to the Deque?
To the front. So it gets explored next. The Deque now has, from front to back, the empty cell, then the other obstacle cell.
You're absolutely right. The algorithm now processes that empty cell, examines its neighbors, updates distances if necessary, and adds any unvisited neighbors to the Deque, always prioritizing empty cells. It continues this way until it reaches the destination cell.
Wow, I see how this approach would be quite efficient. It's like it's intelligently sniffing out the easy paths, avoiding those obstacles as much as possible.
Exactly. And by using the Deque, we're able to achieve that prioritization without the computational overhead of a priority queue, like in Dijkstra's algorithm.
This has been such an insightful walkthrough. I'm really starting to grasp the nuances of these algorithms, but I think we've covered a lot of ground in this part. Perhaps it's time to take a break and come back fresh for the final part, where we can compare and contrast these approaches in more depth.
I agree. We've delved deep into the mechanics of both Dijkstra's algorithm and the modified BFS with a Deque. In part 3, we'll wrap up this deep dive by comparing and contrasting these 2 approaches, discussing their strengths and weaknesses, and exploring some final thoughts.
Sounds like a plan. Join us next time as we conclude our AI.Code.Cast deep dive into the fascinating world of pathfinding algorithms. Welcome back to AI.Code.Cast. It feels like we've just gone through boot camp for pathfinding algorithms.
We have covered a lot of ground, haven't we? We did a deep dive into both Dijkstra's algorithm and that optimized breadth-first search with the Deque, even applying them step by step to our example grid.
Right. And now that we have a good understanding of how they work, I'm curious to compare and contrast them. Like, when would you choose one over the other?
That's a great question. Think of Dijkstra's algorithm as the veteran explorer, reliable, adaptable, and guaranteed to find the absolute shortest path in any weighted graph.
Okay.
Whether those weights represent distances or costs or anything else, Dijkstra's can handle it. It's like the Swiss Army knife of pathfinding algorithms.
So Dijkstra's is our go-to solution if we absolutely need the most optimal path regardless of the complexity.
Exactly. But remember that versatility comes at a slight cost. As the graph gets larger, Dijkstra's can start to slow down because of the way it manages the priority queue.
So it's not always the fastest option.
True. But it's important to remember that Dijkstra's always finds the optimal solution. If you absolutely need the shortest path no matter the cost, Dijkstra's is your reliable companion.
Now, how about that modified BFS with the Deque? It feels more like the Agile explorer darting through the grid with impressive efficiency.
I like that analogy. It's specifically designed for scenarios like our obstacle problem where the edge weights are limited to 0 or 1.
Right.
It's like it's hyper-aware of the simple cost structure and uses that to its advantage.
In that prioritization, using the Deque is key, right? It's like the algorithm saying, hey, let's zoom through those empty cells first before we even think about tackling those obstacles.
Exactly. And because it avoids that computational overhead of a priority queue, this optimized BFS can be significantly faster than Dijkstra's, especially as the grid size grows. It's truly a specialist excelling in this specific domain.
But it's not as adaptable, right? If we had a more complex scenario with different edge weights, like maybe some obstacles are harder to remove than others, this approach wouldn't be as effective.
You're right. It's a specialized tool optimized for a specific type of problem. It wouldn't be as versatile as Dijkstra's in handling those more intricate cost structures.
So it's all about choosing the right tool for the job. If you know you're always dealing with grids and obstacles with a simple cost of 0 or 1, the optimized BFS is a fantastic choice. But if you need a more general solution that can handle a wider range of scenarios, Dijkstra's is the reliable option.
Precisely. And that's one of the beautiful things about algorithm design. There's often more than one way to solve a problem, and each approach has its own strengths and weaknesses. Understanding these trade-offs is key to becoming a skilled algorithmic thinker.
I couldn't agree more, and I think this deep dive has really highlighted that idea. We've seen two distinct approaches to the same problem, each with its own elegant logic and efficiency considerations.
It's been a truly insightful exploration, and I hope our listeners have not only gained a deeper understanding of these specific algorithms, but also a greater appreciation for the power and creativity involved in algorithm design.
Absolutely. And before we wrap up this episode of AI.Code.Cast, let's leave our listeners with a final thought to ponder. We've been focusing on navigating a grid, but how could these algorithms be applied to solve real-world problems beyond this specific scenario?
That's a fantastic question to leave our audience with. Think about any situation where you need to find the shortest path or optimize a route. It could be routing traffic through a city, planning the delivery routes for packages, even guiding a robot through a complex environment. The possibilities are endless.
It's amazing to think that these seemingly abstract algorithms can have such a profound impact on the real world.
It's a testament to the power of computational thinking and the beauty of finding elegant solutions to complex challenges.
Well, on that note, we've reached the end of our AI.Code.Cast deep dive. Thanks for joining us as we explored the fascinating world of pathfinding algorithms.
Until next time, keep coding, keep learning, and keep those algorithmic wheels turning.